right, so it looks like about everyone has joined, so let's start today's meeting. So today we'll be doing an introduction to number theory in the AMC8. So let's start with a fairly basic problem to start today's class. So how many 3-digit numbers are divisible by 13? You'll notice that especially in the AMC8, number theory problems mainly consist of basically division or some other variant of like division basically. So let's start with this problem. How many 3-digit numbers are divisible by 13? So there aren't any specific rules for division by 13, as opposed to like division by 9 or like 11 or 3 or 2 for that matter. So how would you do this problem? So first, let's make a note of something. We know that how many 3-digit numbers exist? Could anyone put that in chat? Yeah, 900 3-digit numbers. So what does that mean? So out of these 900 numbers, we want to find which ones can be written in the form of 13x. Basically, what we're saying is, how many numbers from 100 to 999 are divisible by 13? And we can do that just by taking 900 over 13. And if we were to do this, then we would get that this value is roughly equal to 69. So our answer would be C in that case. Does that solution make sense? So it looks like a couple more people are joining. So let me just briefly go over today's class. So today we'll be doing number theory in AMC8. And we're starting today's class off with problem 18. How many 3-digit numbers are divisible by 13? So what we're essentially asking is how many numbers from 100 to 999 are divisible by 13? So there are several ways to approach this. First way would be finding the smallest multiple of 13 from 100 to 999. And that would essentially just be 13 times 8. If we were to do that, we would get 13 times 8 is equal to 104. And then finding the largest divisor, or the largest multiple of 13. That's less than 999, which is 988. We have 13 times 76 is equal to 988. So that means there's 76 minus 8 plus 1 equals 69 multiples of 13, or 69 3-digit numbers that are divisible by 13. Does that solution make sense to everyone? All right then, moving on. So problem 20, Alice and Bob play a game involving a circle whose circumference is divided by 12 equally spaced points. The points are numbered clockwise from 1 to 12. Both start on point 12. Alice moves clockwise and Bob counterclockwise. In a turn of the game, Alice moves 5 points clockwise and Bob moves 9 points counterclockwise. The game ends when they stop on the same point. How many turns will this take? So basically this is, essentially a clock. 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 right here. So this is roughly what the circle looks like. And they both start at point 12. Let me just do that in red. So Alice, A, moves counterclockwise, while Bob, B, moves clockwise. Bob moves counterclockwise, Alice moves clockwise. So if Alice moves 5 points clockwise and Bob moves 9 points counterclockwise, the game ends when they stop on the same point. How many turns will this take? All right, so let's first do an experimental run of this. So they both start at 12. Yeah, it's kind of like mods. But let's first just do an example turn of this. So if Alice moves 5 points clockwise, she does 12 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. And then she ends up on 5. And then Bob, on the other hand, who is green, let me just erase this and redo this in green. Bob moves from 12 to 11 to 10 to 9 to 8 to 7 to 6 to 5 to 4, and then he ends up at 3. So Bob ends up at 3, Alice ends up at 5. So we could do this another time. 3 to 2 to 1 to 12 to 11 to 10 to 9 to 8. And then all the way to 6. And then Alice, on the other hand, she moves from 5, 6, 7, 8, 9, 10, basically. So once again, they land on different points, 10 and 6. So we could do this for a while, right? We could do this for at least 6 turns, but then that would be pretty time consuming and that wouldn't be the best way of approaching this problem. So alternatively, we can do something else. So you know they both start on 12. And the idea is using mods or a division essentially to do this problem. So we can write Alice's turn as something like this. So Alice's turn is 12 plus 5x. And then Bob's turn is 12 minus 9x, where x is a number of turns. And then we're basically saying that at some point, 5x is equal to negative 9x plus some multiple of 12, plus 12 times n. So at some point, if we were to write this in mod 12, then we can do this. Alice's turn is equivalent to 5x mod 12. Bob's turn is equivalent to negative 9x mod 12. And then at some point, 5x mod 12 is equal to negative 9x mod 12. And the reason why there are 3 lines here, it's not a regular equal sign. It's 3 lines means equivalent. So let me just erase this since this is kind of in the way and it's useless now that we've moved on to mods instead of using the diagram. Now we say this. So we have some number x such that 5x is equivalent to negative 9x mod 12. So then that means that at some point 14x is equivalent to 0 mod 12. So that means that at some point 14 times some number x is divisible by 12. So you know that 14 itself is divisible by 2 and 3, so that means that as long as x is some multiple of 6, then we're good. So if we were to check, if x is equal to 6, then 14 times 6, which is equal to 84, is indeed a multiple of 12. So our answer would just be 6. Does this solution make sense? And does anyone have any questions about mods? So let me actually just briefly explain what mods are. So mods, if we have some number m is equivalent to n mod p. Mod p, not MDP. Then this essentially means that m is equal to n plus p times some number q. N is basically the remainder when m is divided by p. That's what a mod means, right? So does that make sense? All right, since no one is talking, then I'll assume it does make sense. All right. So let's move on to problem 24. So we have a certain calculator that only has 2 keys plus 1 and times 2. When you press one of the keys, the calculator automatically displays the result. For instance, if the calculator originally displayed 9 and you press plus 1, then that would display 10. If you then press times 2, it would then display 20. Starting with the display 1, what is the fewest number of keystrokes you would need to reach 200? So it looks like some people have an idea how to do it. So how about this? I'll actually give y'all like 30 seconds to like briefly contemplate how to solve this problem, and then I'll go over it. Sure, Michael, if you want to explain it, please explain it. You can also unmute yourself if you think that's easier way to explain it. Maybe in like another 30 seconds, just wait, or like you could type up your solution in chat, I guess, if you prefer writing in chat, or just like, yeah, right. Yeah, that's also how I did it. So essentially what Michael means is let's start with the number 200. There are multiple ways how you could get from like 1 to 200 using like plus 1 or times 2. You could do like plus 199 times. You could just do like times 2 times 2 times 2 times 2, so on and so forth until you get 128, and then you just add like 72 times. But the easiest way to do this would actually be working backwards. So first what you do is you take 200 and then you divide by 2. 100. Because that's the fastest way to get from some number to 200, just like multiplying 100 to 200, that's like the fastest way. You only need 1 keystroke. And then you go from 100 to 50. Because if you remember, if you go from 50, you only need 1 keystroke, which is times 2 to 100. We do the same thing with 50 to 25. So 25 times 2 times 2 times 2 is the fastest way, or like the shortest way, since you only need 3 keystrokes to get to 200. But unfortunately, 25 is odd, so you can't just divide by 2 again. So what you do is minus 1. So then you would get 24. 24 is like the fastest way you could get from any number to 25. That's only one keystroke. Similarly, we divide by 2 again, so that would be 12, 6, 3. 3 is odd, so we get 2 instead, and then 1. So we go from 1 times 2 or plus 1, add another 1. So that would give us 3 times 2, 6 times 2, 12 times 2, 24, plus 1, 25, so on and so forth until you get B. All right. So does everyone understand that solution? All right. So let's look at problem 20 then. A singles tournament had 6 players actually. Each player played every other game only once, with no ties. And by the way, the discussion about buying a calculator with only 2 buttons is great and all, but let's move on to problem 20. A singles tournament has 6 players. Each player played every other player only once, there's no ties. If Helen won 4 games, this dude won 3 games, Janet won 2 games, and Kendra won 2 games, and Laura won 2 games. How many games did Monica win? All right, so there are multiple ways you can do this. So we have 6 players, right? So we have H, we have I, we have J, we have K, we have L, and we have F. So we could just like consider the matches between each player and so on and so forth, but that would be pretty tedious, right? So the simplest way to do this is that we know there's a fixed number of wins in total. Yeah, it's a pretty easy problem. We know that since the tournament has 6 players, and each player plays every other player once with no ties, then that means that there are a total of 6 choose 2, which is equal to 15 games. All right. So then from here on out, we know that Helen won 4, Ines won 3, Janet won 2, Kendra won 2, and Laura won 2. So if we just do this, 15 minus 4 minus 3, 15 minus 4 minus 3 minus 2 minus 2 minus 2, then we get that Monica won 2 games. Does that make sense? Looks like most people already did this problem before. Yeah, there's a total number of wins of 15. All right, so let's look at problem 23. So a box has several gold coins. The coins are equally divided among 6 people, with 4 coins left over. So the coins are divided among 5 people, with 3 coins left over. And then the box holds the smallest number of coins that meets these 2 conditions. How many coins are left when equally divided among 7 people? All right, so let's look at this problem. We can actually use mods to do this problem because look at it like this. So you have a box that contains like X amount of coins. X is equivalent to 4 coins mod 6. It's also equivalent to 3 coins mod 5. Right, good job y'all in chat. So essentially this is what we have was working with to work with. So there's actually a way to do this. So what you do is basically say that write X in terms of 6 and 4 and write X in terms of 3 and 5. So we know that X has a remainder 4 when divided by 6. So we can write x as this. X is equal to 6m, where m is a quotient plus 4. It's also equal to 5n plus 3. So we have this, right? This also kind of looks pretty ugly, actually. We have one equation and two unknowns. However, we can do something like this. 6m plus 1 equals 5n. And what's the smallest possible x, or what's the smallest possible n and m that satisfy this equation? All right, so can anyone put that in chat? Right, so it looks like a lot of people agree. So if m is equal to 4, then that means that we have 24 plus 1 is equal to 25 is equal to 5 times 5. So then that means that n equals 5, m equals 6. So if we were to plug this back in, m equals 4, not 6, m equals 4. So if we were to plug this back in into this equation, then we get that x is equal to 25 plus 8, or 24 plus 4, which is equal to 28. 28 divided by 7 is 0. So you get A. All right, good job, y'all. Yeah, there are many ways to do this. Using 6m plus 4 and 5n plus 3 is one such way to do it. I think it's actually the easiest way to explain it using mods and algebra. All right, so mods essentially is a way of expressing a number. So let's say we have a number n is equal to r mod p. Then that means that when n is divided by p, then the remainder equals r. Wait, I said the remainder is 0. By the way, if you're confused about what I just said, I said the remainder is 0 since 28 divided by 7 is 4. So the remainder is 0, so there's none left over. Right, if I ever said 27 divided by 7 is 0, then sorry, that was not my intention. I meant to say 28 divided by 7. All right, so let's look at problem 25. Barry wrote 6 numbers, one on each side of 3 cards, and laid the cards on the table as shown. The sum of the 2 numbers on each of the 3 cards are equal. The 3 numbers on the hidden sides are prime numbers. What is the average of the hidden prime numbers? Yeah, by the way, I meant to say 28 over 7. Yeah, I'm pretty sure I also said 28 over 7, which has a remainder of 0. All right, moving on to problem 25. So y'all all understand that basically 28 divided by 7 has a remainder of 0, so our answer is 0. That's essentially the problem. All right, problem 25. We have 6 numbers, one on each side of 3 cards, and lay the cards on the table as shown. Although we've done this problem before, I think it's pretty prevalent for number theory. So basically, this is a problem that can be solved using parity. Yeah, the middle one has to be 2, right? Remember this from like our last class? Basically, using parity, which is determining if the answer has to be odd or even, is like a crucial way of doing number theory. So I think we'll just do like a really quick review of this problem since we've already done it before. So essentially, the sums of the 2 numbers on each of the 3 cards are equal, and the other side of these 3 cards are all prime numbers. Oh, by parity, I mean to say it like this: parity. Parity is like determining if a number is even or odd. So we know that the number on the other side of 59 has to be 2. Since all prime numbers are odd except for 2, so if we have like 44, wait, all right. So essentially it goes like this. We have 44 plus x is equal to 59 plus y is equal to 38 plus z. Yeah, if y is an odd number, then that means that we have 59 plus y is an even number. Then that means that 44 plus x is an even number as well, and 38 plus z is also an even number. However, only one of x and z can be even. Since the only even prime number is 2, so then that means that x and z have to be odd, and y has to be even. The only even prime number is 2, so then we get y equals 2. So from there, we can get that x is equal to 61 minus 44, 17, and that z is equal to 61 minus 38, which is 23. So then 23 plus 17, that would give us 40, plus 2, that would give us 42. Divide by 3, that would give us 14. So that's our whole solution. So essentially what we did is using parity, determining whether y has to be even or odd to solve this problem. It's pretty important. It's a pretty important concept in number theory problems. So that's why I included it in today's handout, even though we went over it before, just as a short reminder. So now we have this. Let A, B, and C be numbers with 0 is less than A, is less than B, is less than C. Which of the following is impossible? Yeah, so it looks like a lot of people agree it's A. So what you do here is we know that C is greater than B. So then we also know that A is a positive number. Yeah, you could substitute it. Or alternatively, since some of these conditions can be done without using, well, A, B, and C less than 1. So essentially what we do is positive numbers are bounded under addition. What that means is A plus C is bigger than 0. And since we know that, and we know A plus C is bigger than C. So A plus C is bigger than C is bigger than B. That's our whole solution. Does that make sense? Yeah, what we're essentially saying that is if A plus C is bigger than C, then that means it must be bigger than B as well. All right, moving on to the next problem. The product of two 99-digit numbers, these two numbers, has thousands digit A and units digit B. What is the sum of A and B? All right, so for problem 18 is actually a pretty interesting problem. I'll give you like 1 minute to do it. All right, so we have a bunch of different answers in chat. Some are saying B, some are saying C, some are saying D. A and E feel very left out. So let me give you like maybe 15 more seconds and then I'll go over it. Remember when it says thousands digit, that means that it's the thousands place, not the hundreds place. All right. So when we're contemplating such big numbers, initially we might be scared, right? However, we only have to care about the thousands digit and units digit of their product. So let's actually look at this, right? 0303 times 0505. If we could determine this product, then we're done with the problem, right? Because any number from here on out, like 30,000 or like 50,000 or 50505, the 3 and the 5 beyond the thousands place don't matter since their product influences the 10,000s and the 100,000s. It doesn't influence the thousands nor the units digit. So let's multiply these two numbers. So you could just like brute force it, right? Or you could alternatively just say it's like 101 squared times 15. 101 squared is just equal to 101 squared is just equal to 10201 and then times 15. Anyways, eventually you'll get 153,015 as a product of 303 times 505. So what's a units digit? It's 5. What's a thousands digit? This is a 10 digit, this is a 100 digit, the thousands digit is 3. So 3 plus 5 is 8. And that's our answer. Does that make sense?
How did you get 153,015?
That's just a product of 303 times 505. The thousands digit is not 0. All right, so I can just like prove this using a calculator, right? So let me just go to, all right, wait, give me one moment. All right, let's pull up a calculator. All right, and what we're doing is 303 times 505. And just to prove it, it is indeed equal to 153,015. The 0 right here, the 0 which is right here, this 0 is a hundreds digit. So to go over some stuff, so if we have 3015, the 3 is in the thousands digit, the 0 is in the hundreds digit, the 1 is in the tens digit, and 5 is in the units digit. Yeah. So as I said, the easiest way to basically multiply these two numbers together would just be doing a 101 squared times 15, since we know that 101 squared is 10201 times 15, and then it's just significantly easier if we do that, since we'll then get 10000 times 15 plus 200 times 15 times 1 times 15. All right, and then if we multiply that together, then we just get this expression. Yeah. Remember to read the problem carefully always. So when I was in middle school and doing AMC8, I remember missing like a couple of questions because I read the problem wrong, and that was very sad and very disappointing. All right, so let's look at problem 19. So pick two consecutive positive integers whose sum is less than 100. Square both of these integers and then find the difference of the squares. Which of the following could be the difference? So this is also a fairly interesting problem. I'll give it like maybe a bit less than 1 minute to do it. Unfortunately, if you were to do 1 and 2, then you would get 2 squared 4 minus 1, which would give us 3. Unfortunately, 3 is not an answer choice here. If 3 were an answer choice here, then that would be pretty easy, and then we would be very happy because that means like it's essentially a free problem. Right. Understand that it might be a little complicated or hard for some people, so let's just wait for like another 30 seconds, I guess, and then I'll go over the problem. Just as a hint, it says consecutive positive integers. All right, so let's look at it. So let's say we have 2 consecutive positive integers. Oh, oops, my pencil just fell off the table. All right. So we have, let's say our first positive integer is n, and we have n plus 1. So let's square them, shall we? N plus 1 squared is plus 1 squared minus n squared. We want to find their difference, right? Right. So n plus 1 squared is n squared plus 2n plus 1, and then we subtract n squared. So we could cancel the n squared and the n squared to get this is equal to 2n plus 1. All right. So our answer is 2n plus 1. So out of these problems, out of these answers, we get rid of 2, B, well, A, B, and D, because 2n plus 1 is always odd. It's basically an even number plus 1, which would give us an odd number. So now we have 79 and 131. So how do we choose which one is correct? Well, we're given that the sum of these two numbers is less than 100. So that means that n plus 1 is less than 100. 100. So that means that 2n plus 1 is less than 100. So then we get that 2n plus 1 must be C, 79. Does that make sense? I think it's a pretty interesting problem. All right, so let's look at, wait, why the plus 1? Okay, so we have 2 consecutive positive integers. So the definition of 2 consecutive positive integers is basically a number and the next number bigger than, so like 4 and 5, or like 17 and 18, basically n and n plus 1. So that's why we have the plus 1, because that means that n and n plus 1 would be consecutive positive integers. Yeah, all right. So, all right, I hope that explains that. So let's look at problem 15. In Teresa's first 8 basketball games, she scored 7, 4, 3, 6, 8, 3, and 1. So in her 9th game, she scored fewer than 10 points, and her points per game average for the 9 games was an integer. Similarly, in her 10th game, she scored fewer than 10 points, and her points per game average, not points per average game, for the 10 games was also an integer. What is the product of the number of points she received in the 9th and 10th games? So I think this problem deserves at least 1 minute of trying the problem. I think this is a pretty interesting problem. There are multiple ways of doing it. You could always bash your head in with guessing and checking. Or you could also do a more systematic approach. Wait, we're actually not told if the average of her games is 10. Basically what it says, in her 9th game, she scored fewer than 10 points. And her points per game average for the 9 games was an integer. The average for her games doesn't necessarily have to be 10. I hope that explains your question. All right, so looks like a couple people in chat are putting B. Let's see if A, C, D, and E will be getting some love. All right, so it looks like a bunch of people have an answer now, so let's go over it. So 7, 4, 3, 6, 8, 3, 1, and 5. So what if we were to sum these 8 basketball games up? So what's 7 plus 4, 11 plus 3, that's 14 plus 6, that would be 20 plus 8, 28 plus 3, 31 plus 1, that would be 33 plus 5. Wait, no, sorry. 11, 14, 20, 28, 31, 32, and 37. Sorry about that. So yeah, the sum of her 8 games is 37. So in her 9th game, let's say that she scores X amount of points. So 37 plus X, and we know that X is less than 10, by the way. 37 plus X is equal to some integer, let's call it N, times 9. So basically what this means is that 37 plus X is equal to like some multiple of 9. So what's the multiple of 9 that's closest to 37? Well,
36.
yeah, but like X can't be a negative number. Like if she scores -1 points, that would be pretty sad, right? We assume that she scores a positive number, or basically a non-negative number of points. So 45, right? Basically, the next largest multiple of 9 greater than 36 is 45. So that means that 45 minus 37 is equal to 8. So X is equal to 8. So that means in her first 9 games, she scores 45 points. Now let's consider her 10th game. 45 plus Y is equal to some integer M times 10. So what's the closest multiple of 10 to 45? That would be 50, right? So then 45 plus Y is equal to 50. So then that means that Y equals 5. So then their product is 5 times 8, or 8 times 5, which would give us B. So it turns out B deserves all the love, and A, C, D, and E will be shunned. All right, so let's look at problem 22. For how many positive integer values of n are both n over 3 and 3n 3-digit whole numbers? So this is also a very interesting problem. I'll give you like around 1 minute to do it. So the reason why I keep giving you like around 1 minute to do it is so like y'all have some time to attempt it. So when I start explaining things, that makes sense. Because like the later problems in these handouts, in this handout specifically, I think deserve some thought because they're all fairly interesting. All right, so I'm seeing a lot of answers of A and E in this problem. So let's see, who or which answer deserves our love and affection and attention and care? All right, so we have that n over 3 and 3n are whole numbers. So what does this mean? That means that n over 3 is an integer, and so is 3n. So let's say that n is equal to like 3m. Then we're basically asking how many integer values of 3m are both m and 9m whole numbers. Well, what's the smallest three-digit number? That's 100, right? And what's the largest three-digit number? That's 999, coincidentally divided by 9. So then that means that the smallest m can be is 100, the largest m could be is 111. So then we have 111 minus 100 plus 1, that would give us 11 plus 1 is 12. So why is it not 34? Well, if you consider the numbers from 300 to 333, let's consider n is equal to 301. 301 is a number from 300 to 333, right? However, 301 is not a multiple of 3. That means that if we have 301 is equal to n, then that means that n over 3 is not equal to a whole number, if that makes sense. So then we can't take every number from 300 to 333. We can only take the multiples of 3. Yeah. E deserves our hatred because it tricked a lot of my precious students. All right. So our answer is indeed A. Okay, so let's look at problem 16. How many three-digit positive integers have digits whose product equals 24? So let me just give you like around 30 seconds to do this problem, and then we'll go over it. Okay, so I think some people, I think you'll need a bit more time, so I'll give you like another 30 seconds, maybe to do this problem. All right, so I see a C, A, and D in chat. So let's see, who deserves our love? So we have 3 positive digit integers how many 3-digit positive integers have digits whose products equal 24? So 24 is equal to x times y times z, where x, y, and z are all less than 10 because they're 1-digit numbers, right? So this is kind of a combo problem, really. So like Andrew said, basically what we can do is we know that 24 is equal to 2 cubed times 3. So then we have that then we can do some combinations of integers. 1, 3, 8, 1, 4, 6, 2, it would be 2, 3, 4, and 2, 2, 6. So this would give us 6 combinations, well, 3 factorial really. This would give us 3 factorial. 6, this would also give us 3 factorial. And then this one, 2 to 6, would give us 3 factorial over 2. So that would give us 3. So then that would give us 18 plus 3 is equal to 21. So that's a great approach and all. So now let's look at problem 17. So we have positive integers x, y, and z. Wait, sorry. We have positive integers x and y. There's no z actually in this problem. Where the smallest positive integers, 2 smallest positive integers, for which the product of 316 x is squared and the product of 316 y is a cube. What is the sum of x and y? So, as I said, for like the past 6 or 7 problems or so, this is a very interesting problem, and I'll give you like around 30 seconds to do it since we're kind of running short on time. All right, so it looks like a bunch of people agree that it's B. So we have that 360x is equal to some number m squared, and we have 360y is some number n squared. So let's first prime factorize 360. As someone put in chat, 360 is equal to.
Isn't it n cubed?
Wait, did I not write n cubed? Oh, okay, I'm so sorry. This should be n cubed. 360 is equal to 360 is equal to 2 cubed times 3 squared times 5. So what are we missing? in order to express 2 cubed times 3 squared times 5 into a cube, then we have to multiply this by 2 and we have to multiply this by 5, because then that would give us 2 to the 4th and 5 squared, so that would give us some number squared. So the first number would be 2 times 5. All right, so now let's look at consider where we have n cubed, or 360y. So what is y in this case? Well, if we multiply 360 by 3 and we multiply it by 5 squared, then we'll get that this is equal to 3 cubed times 5 cubed, which would be some number cubed, right? We don't really care what n and m are, but we do care what y is. Y is equal to 75, x is equal to 10. So let's sum them up to get 85. So it turns out our answer is B. So one last problem of the day before we end. So problem 22, how many whole numbers between 1 and 1000 do not contain the digit 1? All right, so problem 22 is kind of a combination of a combo and a number theory problem. So what we do is we consider all the numbers between 1 and 1000 that do contain the digit 1, and then we subtract those numbers. So how do you define a number to have 1? Well, let's first start with number 1. And the reason why I'm not giving you time to do this is because we have like literally 1 or 2 minutes left of class. It's like it would kind of be a waste to give you like 1 minute to do it. All right. So how many one-digit numbers, or sorry, how many one-digit numbers have a digit 1? So that would be 1. How many two-digit numbers contain the digit 1? So that would be like 10 through 19. So that would be 10 numbers. So 10 and 1. So how many three-digit numbers contain the number 1? That would be 100 to, well, 199. However, we're missing some numbers from the two-digit case because we're missing 21, 31, 41, 51, 61, so on. So 21 all the way to 91. That would be 9 minus 2. That would give us 7 plus 1. That would give us 8. So 18 two-digit numbers. How many numbers from 100 to 1000, or 100 to 1000 contain the digit 1? Well, first of all, 1000 contains the digit 1. So for four-digit numbers, that's 1. How about three-digit numbers? Anyone from 100 to 199? Sorry, that should not be a 0 at the end. But surely you'll want class to last a little bit longer, right? Math is fun. So that'll be 100 numbers. And then we consider all the numbers that are like 201 or 210 or like 211. So for this, essentially we have 1 plus, well, 1 plus 18. So essentially we have 18 times 8. So that would be So that'd be 18 plus 8. 18 times 8, 144, plus 100, that'd be 244, plus 18, plus 1. Wait a moment, what would be 18 times 8? It would be 19 times 8, sorry about that. 19 times 8, 152, plus 100, plus 19. That'd be 271, or 272 rather, and then we would just do 1000 minus that, and then we get D is our answer. Sorry, that's all for today. All right, see y'all next week.
Bye. Thank you.
Thank you. Bye.
Bye. Thank you.
Thank you.